Good afternoon, Prof. I'll be presenting on my term paper, Edge Computing. We all know the cloud enables rapid data transfer, but even is bounded by one universal limit, the speed of light. So how do we close this gap? How can we bring critical data even closer to where it's needed most? Looking at the statistics, it's no stranger that with the rapid proliferation of cloud computing, the cloud computing market is growing year over year at a 17.9% compound annual growth rate. At the same time, there's a huge increase in the amount of data being generated and the number of IoT devices. There is 55.7 billion devices and 80 billion zettabytes of data in existence. While cloud computing is ideal for many large or scalable applications, this trend introduces a new challenge for time-sensitive functions, latency. As a result, there's a growing demand for computational resources closer to IoT and devices, emphasizing a shift away from centralized cloud computing. Edge computing provides a distributed approach to data processing, offloading from centralized cloud servers to devices at the network periphery as illustrated in the figure here. Time-sensitive devices can utilize edge devices to help with time-sensitive functions that the cloud may not be able to support. I'll be reviewing recent research in edge computing technology to support latency-sensitive application in various sectors. By exploring both current trends and challenges in the literature, this review aims to highlight the potential of edge computing architecture. In the first paper, the emergence of edge computing, the key findings are as follows. There's an increased demand for latency-sensitive IoT applications such as AR or AV, and edge computing can bridge the gap between centralized cloud and end users. So the idea of edge computing dated back to the creation of CDNs back in the 1990s. There are four core capabilities of edge computing: low latency, proximity to end users improves real-time responses, bandwidth optimization, local processing reduces network congestion, privacy, local data processing supports compliance with GDPR, and lastly, resiliency, as it can operate during network disruptions. However, there are still some challenges to overcome. Infrastructure management, there's a high cost and complexity in distributed cell. Secondly, the economic viability, you need to weigh between the initial investment versus the network applications. And lastly, scalability, as heterogeneous devices require adaptable architecture, which is really hard to scale. In the second paper, decentralized resource auctioning for latency-sensitive edge computing, the objective of the paper is to address some of the challenges in infrastructure management and scalability. They do so by suggesting an auction-based decentralized resource management technique. The framework is as follows. Firstly, task announcement. A dispatcher will broadcast tasks with resources and privacy needs. Secondly, bid generation. Devices submit bids with latency, cost, and privacy guarantees. And lastly, task allocation, where it's optimized based on multi-objective algorithms. So this results in 95% allocation success rate, but only for small and medium networks. Once again, there are some challenges. Firstly, heterogeneity. So similar to the first paper where it's very hard to balance all of this device diversity. Second, energy overhead because it requires computational costs to do the BD and reallocation. And lastly, once again, scalability. In the third paper, comparison of edge computing implementation, it introduces the various implementation of edge computing that we can consider. Firstly, fog computing, which is decentralized and heterogeneous nodes. Secondly, mobile edge computing, MEC, which utilizes cellular integration or the 5G network. And lastly, cloudlet computing, which is localized high-performance clusters. There are some key differences between them. For fog computing, the strength is in its ability to scale, but it has latency issues. For MEC, it provides real-time decision making, but it consumes a lot of energy. Thirdly, cloudlet computing, it supports high computational power, but it lacks in context awareness. It's recommended to use different implementation based on your needs. For fog computing, it's best for constrained IoT devices. For MEC, it's optimal for real-time context-sensitive applications. And for cloudlet computing, it's suited for computationally intensive tasks. In conclusion, I think that hybrid models which integrate the benefits of fog, MEC, and cloudlet strengths will be essential. We should also explore AI-based solutions such as federated learning to better optimize this framework. And lastly, with such a vast number of end devices, it's important for us to have a standardized matrix for consistent deployment, allowing us to fully utilize the benefits of edge computing. Thank you very much.